Ready to go, Safan? And is it good quality sound so that our friends in like Oregon can hear us and all that? Okay, excellent. Well, welcome everyone to the University of Hawaii Institute for Astronomy Haleakala Division. I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist, which basically means I got a title raise in there somewhere. One of the things I get to do with my job is to bring speakers here to give great talks, and this month I was able to wrangle Tim to come on over here. Dr. Tim Slater, so he's basically dedicated his career to helping people become better teachers. And I think everyone that's been to college has had that college professor that was a really nice person and did great research, but as a teacher, maybe was a little lacking. And so that's what Tim does, is he helps that professor become just a really outstanding teacher. He's conducted hundreds of workshops for thousands of professors to help them become better teachers. He's known as the professor's professor, and he's going to be talking about sort of the history of astronomy and under the topic of Galileo's 21st century syllabus. And let's give him a nice Maui welcome. Okay.
All right. What do I do with this?
You loop that over your ear.
It's going to get stuck in my hair.
Yeah, I know. That happens to me too. Okay.
All right.
And there.
So I put this in my pocket. It's like,
Or whatever. Yep, that's good.
all right, excellent. Thank you, JD.
All right, and just sit down a couple of seconds just to make sure the sound is good.
Say something. Is the sound good? Fantastic. The hardest part's going to be staying here in the light, because one of the things you're going to notice is I tend to run around quite a bit. So if I get out of the field of view and you need me to move, please let me know.
Okay, and well, let me give you something harder then, Tim.
Yeah?
Repeat questions so that the virtual audience can hear them.
Oh, well, I appreciate the idea of repeating questions so the virtual audience can hear them. As it turns out, though, I try to talk really, really fast so no one has a chance to ask any questions. That's generally my strategy here. So, good evening, everyone. It's a pleasure to be here. As JD mentioned, I'm a faculty member at the University of Wyoming. I spent about half my life in Laramie, Wyoming, and about half my life in Hilo, Hawaii, where my wife and I have a sweet potato farm. And so sometimes I'm doing astronomy and sometimes I'm doing potatoes. So I'm either looking up or looking down. Either way, my hands are always dirty doing stuff. But what I'd like to talk to you this evening about is something a little unusual compared to many of the talks that you've probably been attending. And that's to talk not so much about the scientific research that goes on here at IFA, but instead talk a little bit about some of the foundational ideas that have brought IFA to the place that it is. In particular, I want to talk a little bit about this scientist by the name of Galileo. So, let's start with this. So, how many people have heard of Galileo before? Raise your hands. All right, everybody's heard of Galileo. What do you know about Galileo? What's he famous for?
Jupiter and its moons.
He's famous for Jupiter's moons. Excellent. What else is he known for?
The rings.
Known for the rings of Saturn. Excellent. What else is he known for? Being excommunicated. Exactly. And he built the first telescope. What else?
He was cool.
He was totally cool. So this is a lot, right? We got rings of Saturn, we got moons of Jupiter, we got being excommunicated, right? Excommunicate's a big deal, by the way, particularly for people that are deeply religious. The idea of being kicked out of your own church is really not a great thing to have happen to you. He's also famous for experimental physics, right? So not just do astronomy, he also did a lot of things in terms of physics. We'll talk about that in a minute. You mentioned the idea of telescope observations and inventing a telescope. And you mentioned, of course, the idea about being excommunicated. And we're going to talk about all these things because in order to understand who Galileo was and how Galileo has really created the astronomy that we do today, all these things are actually quite important. So what I want to start with is this idea of physics. So even know where this image is or where this building is? It's in Italy. Excellent. It's in Pisa, and it's called the Leaning Tower of Pisa. Excellent. Now, what's the story here? The story is that Galileo was having an argument with people about the nature of gravity and how the degree to which gravity really sucked. And so the story goes that Galileo went to the top of the Leaning Tower of Pisa, and he took a very heavy ball and a very light ball and did what? Dropped them. All right, now, this is unusual because the thinking of the time was if you wanted to know which ball would hit the ground first, the big one or the small one, you didn't actually need to try it. All you needed to do was to think about it. The general thinking of the day was the human brain was the most amazing thing that God ever created. And you should just be able to reason your way and logic your way through ideas. And since the one ball is bigger than the other, gravity must pull on the big ball more than the small ball. And if I drop them at the same time, the big ball should hit the ground first. End of story. That was the idea. You'd actually try to experiment and actually let the data drive your thinking. It was very unusual at the time. And so that's why we often talk about this story. Now, what happened when he did this? They landed exactly at the same time. Now, Galileo wrote about absolutely everything he did. He was a very prolific writer. He never, ever wrote a story about climbing to the top of the Leaning Tower of Pisa. So we actually don't know if this actually happened or not. It probably didn't happen. Because what Galileo did spend a lot of time writing about was eggs, and how do you cook eggs. Because the thinking of the day was, if you took I've lost my handkerchief, but if you were to put an egg inside of a handkerchief and whip it around your head really fast and give it lots and lots of energy, if you did it long enough, you should be able to hard boil an egg. But the idea of actually trying it was not something that people actually did. So one of these most famous experiments that he wrote a lot about was what would actually happen if you took an egg and you started to swirl it over your head. Turns out if you can keep the egg in the handkerchief long enough, the egg will actually cool down, not get hotter. But it's again this idea of experimentation and trying things out, which is what nobody was doing prior to the Renaissance. Now there were lots of cool people doing really crazy things in the Renaissance. Galileo dropping big balls and little balls off the top of the Leaning Tower of Pisa. There was also Michelangelo, who was laying on his back and painting pictures of naked women on top of the Sistine Chapel, right? Also a really bad idea. Leonardo da Vinci was taking dead bodies and cutting them open to see what was inside so we could learn something about how the human body worked. All really bad ideas socially at the time, but really core ideas that formed the Renaissance. The idea we try out new things, think about new things. So you mentioned this idea of the telescope. So Galileo, turns out, did not invent the telescope. He'd heard about the telescope, and heard about the telescope had been created by the Dutch, and he created and built one of his own, just based on understanding what they had done. Now, when I mention this to kids, I say, do you think Galileo invented the telescope? Kids today always say, no, absolutely not. So wait, how do you know whether or not Galileo invented the telescope in 1609? And they say, didn't you ever see the movie Robin Hood? The Moors invented the telescope, because apparently where'd my brain go at this point? Apparently there's a scene in Robin Hood where Morgan Freeman takes the telescope and he's looking around, right? Kids all know about that. They don't know about Galileo. But it turns out Galileo did not invent the telescope, but he was the first person to use it in a particular way. And that particular way was he pointed it to the heavens. And the things he saw in the heavens were shocking to him. So, what Galileo did is he wrote down everything he did. I mentioned this before. And he wrote down his observations about things he saw in the night sky in a book called the Sidereus Nuncius. Now, why was Galileo writing all this stuff down? Well, Galileo was poor. He had 3 children, all illegitimate, but even in those days, there was a certain amount of respect that required you to provide for the dowries to marry off these children. And he needed a job. He needed a patron. And so he wrote this down. By the way, you can get an English version of this on Amazon right now, Sidereus Nuncius. If you're looking for a great gift, Easter's coming up, Mother's Day's coming up. If you really want to impress somebody, get them a copy of Sidereus Nuncius. Tell them exactly who you are. Chicks dig that. He wrote everything down because he was trying to figure out how he could get patrons, how he could get a job. And he eventually did get a job based on his observations. But let's talk about what some of his observations were. He was certainly not the first person to take a telescope and point it up at the sky. But he was the first person to take a telescope and point it at the sky and write down what he saw. And that's what he really gets credit for, is for telling people about the observations. One had to do with looking at the night sky, and in particular, looking here at the Milky Way. when he pointed his telescope at the Milky Way, he saw thousands and thousands of stars. The thinking of the day was, you go outside at night and you look up at the stars, you find a graduate student who has nothing to do, and you say, go count the stars for me. And it turns out there's about 3,000 stars you can see on any good clear night. But with the telescope, he could now see countless stars. And that was really important because the thinking of the day was the universe is a known size, that God made the universe in a particular way of a particular size. And all of a sudden Galileo's saying, wait a minute, the universe is much bigger, much more complicated than anyone had thought before. He also looked at this object. What is this object? Saturn. How do you know it's Saturn? It's got the rings around it, exactly. Now when Galileo looked at this, his telescope was quite small. And he wasn't actually able to resolve rings himself. What he described it as was as a bean with ears. Couldn't quite figure out what it was, a bean with ears. But the thing that he was most curious about was not the rings, but the shape of Saturn. If you look at Saturn, you notice it's not perfectly round. It's a shape called an oblate spheroid, right? It's thicker around the sides and less on top, kind of like me. Kind of got the left handles on Saturn. And the thinking of the day was, when God made the universe, everything in the sky was made of perfect circles. Circles, the most perfect shape of all shapes. And so everything in the sky should be circular. Yet when he looked at Saturn, Saturn was not perfectly round. They say, I'm getting ready to start to build a case here. He's seeing a lot of interesting stuff, but the interesting stuff is starting to conflict with the philosophy of the day. He also looked at this object, the moon. And when he looked at the moon with his telescope, what he realized was the moon's covered with craters. It wasn't just not perfectly round, it was also not perfectly smooth. It had holes in it, which made no sense whatsoever, because when God made the universe all these perfect shapes that are out there. And in fact, when we look close up at the moon today, when we actually go there, we can see there's a tremendous amount of texture on the moon. The moon is absolutely fascinating. Everything that I taught my students about the moon in the last 10 years, completely wrong. The moon has weather. The moon has water. There are water cycles on the moon. The moon is a crazy bananas place. We don't understand much about the moon at all. But then he also took his telescope and looked at this object. What is this? The sun. Now, one of the things that was bizarre about the sun is the sun has spots on it, blemishes on it. Now, I should take a moment here and point out why astronomy, of all the scientific subjects you might study, astronomy is the totally cool one. And that's because, when you take biology, you have to memorize all those Latin prefixes and Latin roots and the names of all the muscles and the bones. It's terrible, that biology stuff. The lab smells bad. In astronomy, we name things what they look like. If there are spots on the sun, they're sunspots. If you see this great red spot on Jupiter, we call it the great red spot. Absolutely. If you look up in the sky and you see stars in the shape of a giant square, we call it the square. Exactly. This is why astronomy is so much easier than those other topics. The great square. But not only did Galileo's sun have blemishes on it, these blemishes tended to move across the surface. So now we're not only seeing an object that's imperfect, but also an object that's spinning. And nothing was supposed to be moving outside the Earth. So coming together, these things are all starting to make a real problem for Galileo. And then you mentioned right from the beginning the moons of Jupiter. So if you take even a small telescope and you look at Jupiter, Jupiter's beautiful and setting in the west right now. It's absolutely gorgeous. Of course, it's cloudy tonight, so you just have to trust me. But tomorrow night, you got to look to the west, you'll be able to see Jupiter. Not till Monday? Oh my gosh. It's like being in Hilo, rains all the time. So if you look at Jupiter through a small telescope, you'll notice that Jupiter always has these little stars next to it, these little dots. And these little dots don't just stay in the same place, they move. For example, if you were to look at it on Monday when it's clear, maybe it might look like this. You go back out Tuesday night and you look at it. Now, you had 4 dots before. Now those dots have moved. Maybe you only have 3 dots visible. You go out the next night and you look at Jupiter. Now you got 4 dots again, but now they've changed their positions. Now, of course, what we know, what Galileo didn't know at the time, was these are not little stars. These are moons. These are 4 of Jupiter's largest moons. And as they go around the orbit, or go around Jupiter in their orbit, they change position. Now, the reason this is interesting is because when people had previously suggested maybe the planets go around the sun, people said, well, the planets are moving really, really fast. There's no way that those moons could keep up with Jupiter as Jupiter goes around the sun. And we already know that since God made man, and man is their most perfect creation, where in the universe are you going to put this most perfect creation? Right in the center. And everything has to go around it. Right? But here's a situation where the Earth is not the center of all rotations. You've got these silly moons going around Jupiter. So when you put all these things together, we've got a bizarre, bizarre situation. But here's the piece that really was most influential. And these are pictures of Venus taken from the Earth. Notice sometimes Venus appears perfectly round and tiny, and sometimes it appears as a slender crescent and really large in the sky. Now, here's the problem. The thinking of the day was that the Earth is at the center of the universe, and that Venus must be orbiting around the Earth. Well, if Venus actually orbits around the Earth, that means, and since we also know that Venus is always close to the sun, because you only see it at sunrise or sunset, you never see Venus at midnight, unless you're a Harry Potter fan and they have the magic brass telescopes that do see Venus at midnight. That's a whole other issue. But we'll come back to Harry Potter here. Is that if you're on the Earth and you're looking at Venus, which is going around the Earth along with the sun, you always see the dark side of Venus. Or if you can see any of Venus at all, you're just going to see a narrow crescent. You're never going to see Venus as a full Venus. Yet, that is what we see. When we go out and we look, if we're on Earth, if we imagine Venus goes around the sun instead of around the Earth, then sometimes we see a crescent shape, which is really big because it's close to us, and sometimes we see give us a full Venus, where it's much smaller because it's farther away. For Galileo, this was the final piece of evidence that said, you know what? We don't live at the center of the universe. The Earth must be just like any of the other planets going around the sun. And the sun must be just like those little white dots we see in the night sky, just like all the other stars. And maybe there are planets around them too. So not only are we not in the center of the universe, we're not in the center of the solar system. We're just like any of the other planets going around. We're not necessarily special. Our star isn't special. So we could be just like any of the other stars out there with their planets going around. And he really de-elevated the special position that humans had in their own minds in the day. And this is what eventually got Galileo excommunicated, as we talked about, which is kicked out of the church. Now, don't worry, Galileo was recommunicated back in 1992, so we're all good now. So these are kind of the big the big six observations. And if Galileo were teaching a class at the University of Pisa and you went to one of Galileo's classes, these would be the 6 big ideas that Galileo would teach. But the question is, let's suppose Galileo was here on Maui in 2018, time travel, right? 2018, what would Galileo teach today? Would he still teach these same 6 ideas? Or would he have a whole new set of ideas that he should be teaching about? Well, I teach introductory astronomy to about 800 students at a time. I teach one of these great big giant lecture halls, right? Doesn't look at all like I'm talking to cardinals and bishops and this sort of thing. These are what my students look like. In fact, this is my classroom here. You can see looks like a giant amphitheater. It's a brand new classroom. It's high tech. It's really designed for student engagement and student learning. I mean, no one's ever really imagined a classroom like this ever before. Well, maybe somewhat before. This is a similar classroom to mine. Anyone recognize this one? It's not the Colloquium, good guess though. It's Ephesus, excellent. I've given this lecture 10 times. You're the first person to notice this was Ephesus, which is in Turkey, all right? Some people say, oh, that's not Ephesus, that must be a Greek theater, right? No, these are theaters in Greece. These are on the island of Delos, right? So that's what these theaters look like. But it's not the Greek theater. Remember, the Greek theater is not in Greece. The Greek theater is in... No, Ephesus is Turkey. No, almost. No, you're right. This is true. But the traditional Greek theater is actually in Sicily, right? And this is Mount Vesuvius here in the background here. So, as you can see, maybe my new technology classroom that my university paid $1 gazillion for is not as new and innovative as one might think. So what would Galileo's syllabus look like? Right? Because remember, you think about your class syllabus you had the instructor's name, right? Now, where would his office be? Remember, Galileo actually had spent the last 8 years of his life under house arrest, was not allowed to leave the house, so his office would have to be at home. There would be a required textbook, of course, and my suggestion is probably Sidereus Nuncius, since that's the most famous book that he wrote. Though today he might use a more modern astronomy textbook. My wife and I have written this one here, so in case you're in the market for a good astronomy textbook for your students, that just might make a quick suggestion there. Now I should point out, this is not the same materials that if a student goes to Hogwarts, they would have to get. If you go to Hogwarts, every student in their first and fifth year is required to take astronomy. And these are the kinds of things they're required. They need brass scales, a magic brass telescope, vials, moon charts, glass vials, star charts, moon globes. And of course you get all these at Wiseacres, wizarding equipment. See the telescope up here. You can go visit a mock-up of Wiseacres if you happen to go to Orlando to Universal Studios or Hollywood Universal Studios. They have mock-ups of these things. So Galileo probably wouldn't require you to have any of this stuff at all. But what about these big ideas? Well, let's go back and look at them for a minute and see if they're outdated, if they are still really important. So where I want to start is I want to show you a very short video here. I have to take off my microphone in order to do this, of what some of my students think about the world of astronomy. So.
What is our galaxy called? Galaxy 500. No, that's a Ford car. Okay. And you guys are graduating from high school this week?
No, it's June 16th.
June 16th, so you should know a lot of stuff.
Oh, we know a lot.
What is our galaxy called? It's also a candy bar.
Mars.
What's our galaxy called? No, I'm sorry, that's wrong. I don't remember. Okay, let me give you a hint. It's the name of a candy bar. Babe Ruth. It's Babe Ruth. Yes, it's the Babe Ruth galaxy. Very good. How many planets in our solar system?
There's like, 12 to 50, I don't know.
12 to 50?
Yeah, it could put it in that, I'm not even saying.
No. How many planets in our solar system?
Oh, let's say 100. I don't know.
100?
I have no
Now,
idea.
did I hear you just graduated college?
I
When?
did,
When,
but I
this
didn't
week?
study astronomy.
How many planets are there in our solar system?
Or was it 12?
How do you,
7?
how do you say no in German?
Da?
Da.
I don't know German.
No, 9.
9? Oh, I was close.
How many planets are there?
9.
Right, very good. All right, what's your name? Eugene. Eugene, you're from Chicago.
Chicago, the Bulls.
That's right, which is in Chicago.
Yeah.
Which constellation is the Bull?
You got me.
There's a car named after it, the Ford.
Oh, the Mustang.
I am an exhibit developer at the Adler Planetarium.
Oh, so you work in a planetarium? This
Yes,
is
I do.
perfect. Which of our planets is furthest from the sun?
Jupiter. I mean, Pluto.
What planet is furthest from the sun?
Venus. Mars.
All right, what's the name of Mickey Mouse's dog?
Goofy.
All right. So now I should point out, when I teach astronomy, I teach at 8 o'clock in the morning, Monday, Wednesday, and Friday. But for some reason, I don't have nearly as many students on Fridays as I do the rest of the days. I haven't figured that part out. All right, so my students that I work with don't already know Galileo's fundamental observations from 400 years ago. So for me, I've got to teach my students this stuff. They don't already know it. But there's so much cool stuff going on in astronomy. I mean, how do you resolve this notion that there's all these wonderful things out there, but students still don't know some of the basics? So I'm going to argue that these things are still important. They're still very fundamental. But maybe we can massage them a bit to do match the kinds of things we know about. So for example, one of the things that Galileo found when he took his telescope and pointed at the Milky Way, that the universe was really big. There are many more stars out there than we ever thought before. But of course, if you look at this picture, this is the Hubble Deep Field image. These little dots here, each of these little dots are not stars. Well, you're right, Sarah. There's a star there. That's in the way. It's in the field. Everything else here, all these little dots are not stars. They're galaxies. Each one of these little blobs here is hundreds of billions of stars gravitationally bound together. So it's not just that our galaxy is bigger than we thought, but our entire universe is much bigger than we thought. When Galileo looked at the moon, he saw craters there. Well, now we've been to many other planets, and we know that other planets also have craters. For example, so this is a picture of the moon and a picture of the planet Mercury. By the way, which is which here? Which one's moon and which one's Mercury? I want you to with your hands here, point either this way or this way. Which one is the moon? All right, you're right. The moon is on the right. The moon is on the right. And that's a couple of things about it. First, the moon's a little bit smaller than Mercury, but not very much smaller. In fact, Jupiter's largest moon, Ganymede, is actually bigger than the planet Mercury. So sizes and everything. The difference here is when you look at the moon, you see these black splotches on it, the maria. These are places when there's been a giant impact craters come in, it basically cracked open the surface, and lava has flown out onto the surface and smoothed things, giving these dark areas here. Now, Mercury doesn't have any of these maria. In fact, even the backside of the Earth's moon doesn't have maria. Maria is a phenomenon we only see on the Earth side of the moon. Now, of course, the moon isn't the only place we see craters. Mercury isn't the only place. This is the Barringer crater, exactly, outside of Flagstaff, Arizona. This thing's about a mile across, 600 feet deep. You can see the line here. This is a road going here, and this is the visitor center. Give you a sense of the enormous size of this thing. This thing's about 40,004 years old. Now, you say, 40,004, how can that be? Well, I was actually visiting, my wife and I, we took the kids, and we visited this place about 4 years ago, and the guy said it's about 40,000 years old. So, and if we actually look at the worldwide distribution of where you find these craters, we see another interesting pattern. So, the interesting pattern, first of all, the interesting pattern we see is that there appear to be no craters that we can find anywhere in this blue area here. Why is that? They're hidden by the ocean, exactly. Are they there? You bet they are. We can only imagine that the number of meteors that hit the Earth, asteroids that hit the Earth, probably hit the Earth pretty much evenly. Yet, we don't find them in the oceans because they're hidden from us. We can find about 127 of these things around the Earth. The one that's most interesting is this one out here outside of the Yucatan Peninsula, which happened about 65 million years ago. This is the one that probably killed off the dinosaurs, as well as 80% of everything living in the ocean and 90% of everything living on land. It was a huge mass extinction. But the Earth isn't just the only interesting one. This is Io, one of the moons. It's the moon that's closest to Jupiter. And when we look at Io, by the way, kids call this the pizza moon because it looks like a cheese pizza, I guess. But one of the things, if we look along the limb here, we can actually see these plumes of material being ejected. Right now, on Io, there are about 11 active volcanoes going on the surface. And much of this work is done over at Mauna Kea at the IRTF. These images here are all spaceborne images, space probes. You can get a sense of how just cool these things are. Not cool, they're hot, but very, very cool looking. Or if we look at Mars, we see some other interesting things going on the surface. For example, these craters here, and here, if we look at the land around them, it looks like, well, this teardrop shape suggests to us that sometime in the past, water was flowing across the surface here and actually eroded out around these craters. I mean, there's lots of evidence of water on Mars. For example, here's a cliff face here. And what we see when we look at the side of a cliff, we see all these patterns here where it looks like water has been flowing downhill, causing erosion into the side of this cliff on Mars. Here's another example of these gullies that we see here when we look at the side of Mars. I mean, Mars looks like it's had water in the past. One of the things is, if we look at these structures like this, these rills, we call them, they look sinusoidal. They look just like rivers do on Earth as they meander around. But here's one that's particularly cool. So we think a lot of the water on Mars is probably frozen beneath the surface in the permafrost. Well, here we have a giant crater, and at some point some huge asteroid came slammed into Mars, and when it did so, it generated a lot of heat, probably melted the area around that crater, and what we see is it caused mud flows to move out. So we don't see any water today, but maybe it's right beneath the surface. A lot of the things we see there suggest that. There's also a surprising amount, just like on the moon, surprising amount of weather that goes on Mars. These are giant volcanoes here called the Tharsis Ridge, and we can see clouds forming. And the fact you see all the clouds forming on one side tells you there must be wind moving across the surface of Mars. This is all really fine and good, but still the best evidence of whether or not there's water on Mars comes from data like this. All right, so what I want to argue here is it's not just the moon has craters, but the entire solar system has active geology going on. And the moon is really cool, but there's other things to look at as well. All right, what about the spinning sun? Well, we already talked before about sunspots, and that sunspots exist. What we now know about sunspots, and you've probably heard a lot of talks here about sunspots, because this is one of the best places on the entire planet to study the sun, are these sunspots are relatively dark regions or relatively cool regions on the surface of the sun. Surface of the sun is about 6,000 degrees. Yes, even at night, about 6,000 degrees. These areas here are hot too. They're about 4,000 degrees. And that difference here makes them look dark in color. If you were there, they'd look really, really bright. But they look dark compared to the rest of it. But in addition to the sunspots, if you look at the area above the sunspots, the atmosphere above the sunspots, we see these huge explosions that occur. You can see this giant ring here, where you've had a bunch of material ejected off the surface of the sun, but the sun's strong magnetic fields curve it into into an arch shape. Thank you very much. An arch shape. But here's what's really cool. So one of the things we can do is, if we want to look at the outer atmosphere of the sun, the best time to do that's during an eclipse. And see, anyone go to the mainland for the eclipse? You guys did? There you go. There's my eclipse chasers. Was it clear? Yeah. Okay, excellent. Excellent. My family was in Casper, Wyoming, of all places, which was kind of cool. We're sitting there waiting for the eclipse, and all of a sudden the deer and the antelope start playing in the front yard. It's very, very crazy. Anyway, so scientists love an eclipse, but eclipses are hard to come by. You got to travel all kinds of places. Last total solar eclipse here was 96, 91? 91 was the last one here. And for many of the islands, places, it was cloudy. So what scientists do is they're very clever. What they do is they create an eclipse. So this is an image taken from a spacecraft called the SOHO spacecraft. And what they've done is they've taken a metal disc and put a metal disc in the middle of the telescope to block out the sun. Now this disc here is about 3 times bigger than the sun is. This little white line here, that's actually the size of the sun. So we have to block out a pretty big area to be able to see what's going on in the outer atmosphere. This dark line you see here, that's the bar that holds that little disc in place. And it allows us to see what's going on as we look around the outer atmosphere of the sun. And what we see is incredibly active. These huge explosions on one side and the other side. A couple other interesting things to see in this image. One, you can see the Milky Way coming across here, across the background. These are little white dots here, all stars that you can see. Really, really neat stuff going on in this image. Now, one thing that the kids always point out to me is they say, wait a minute. When I look at this, if I look right here, there's some sort of giant thing that goes flying into the sun, causing a huge explosion on the other side. Do you see that? Yeah, it's a comet, exactly. Comets are these, little things that are about 10, 15 miles across, 10 or 15 miles across. They're made of mostly ice and dust and rocks. If you want to think about what a comet is, back in Laramie, Wyoming, where I teach, we have these things called shaved ice. Shaved ice. It's very strange. And what happens is you take this big thing of ice and you make it into a ball, and you pour all these kind of good sugary sweet stuff on it. Well, the problem is sometimes it falls out of the cup onto the ground. And if it falls out of the cup on the ground, you go down, you pick it all up, and you stuff it all back into the cone. Now you can't eat it because it's got full of junk in it, right? That's exactly what a comet is. It's kind of like a shave ice that's got a bunch of dust and rocks and stuff in it. Well, it turns out people were amazed when they watched this little 10-mile diameter thing, which was glowing because the sun was shining on it, go smashing into the sun. They said, oh my gosh, who has ever seen a comet crash into the sun? This is the most amazing thing we've ever seen. Let's go see if we can find another one. And they go back the next day, and guess what they see? One crashing into the sun. They go back the next day, what do they see? one crashing into the sun. About 300 times a year, a comet crashes into the sun. But we'd never been looking for them before because the sun is so darn bright and so hard to study. So one of the cool things about studying the outer atmosphere of the sun is we've learned a lot about comets in our solar system. In fact, when these huge explosions happen on the sun, I'll turn that down here. When these huge explosions happen on the sun, an enormous amount of material is ejected into outer space. It takes about 3 days for that material to get here to the Earth. And when the charged particles get here to the Earth, they get captured into Earth's magnetic field. Earth's magnetic field really protects us from the harmful charged particles that come from the sun. Now, some of them do sneak in and get inside to where close to the Earth, and when that happens, it causes the sky to glow. We call this the Aurora Borealis, exactly. Unless you're in Australia, with a fancy accent, you call it the Aurora Australis, exactly. When these things impact the Earth, when these huge explosions of material impact the Earth, all kinds of crazy things happen. Sometimes we understand them well, sometimes we don't. But space weather is a pretty important part of what's going on in the nature of the Earth. In fact, here's a short video from the International Space Station flying over the northern hemisphere, and you can see the aurora. They're actually visible from the space station. It's phenomenal stuff. So it's not just that the sun has spots on it, but the sun really does have tremendous impacts on Earth through space weather. All right, let's keep going here. Before we say about Saturn, remember Saturn's got love handles on it. Is that the thing that students need to know? Well, the answer is yes, right? That all the outer planets have this odd shape to them because when they spin round and round, the outside gets pushed out more because of centrifugal forces. But the reason he was able to make these observations was because, as you mentioned, this telescope. He was able to build a telescope, build a whole series of telescopes. In fact, today we have some pretty cool telescopes, right? Now, most of the telescopes I'm familiar with are over on Big Island. These are the telescopes near the summit of Mauna Kea. But what you're most interested in, of course, are not these telescopes, but these telescopes over here. What is that? That's Maui, exactly. It's Haleakala. And, of course, you can go up here to Haleakala. If you haven't had a chance to go up to the summit, it's really, Science City up there is just really, really totally cool. And there's a lot of neat stuff going on up there. So our own J.D. Armstrong, spaceman, according to Maui Magazine, has been doing a lot of work, not just to glorify himself, but actually doing a lot of work with students. In fact, some of those students are here. We're helping them make observations of extrasolar planets, asteroids, variable stars. All kinds of really neat things are going on at Maui. Not just stuff that results in publications and fancy books, but also things we think really probably change kids' lives in many ways. But it's not just telescopes that look in the visible light. We can actually use telescopes across the entire spectrum of energy that's emitted by shining stars. So you've probably seen this picture. This is a picture of the constellation of Orion. Okay, this is what it looks like in visible light. This bright red star here is Betelgeuse. We can argue about how to pronounce it, how to spell it, and what it means, but that's a whole other talk. Bright star here is Rigel. Excellent. I'll keep you going here. Bellatrix. Excellent. Bellatrix Lestrange. Back to our Harry Potter reference. How about this one? Safe. Excellent. Oh, you guys are great. I'm going to keep pushing you here. Mintaka. Excellent. What's interesting about Mintaka? It sits on the celestial equator. It's exactly 0 degrees, right? So the navigators, this of all the stars here in the Big Dipper, this is the most important one to the Hawaiian wayfinders, because this one tells you when it rises directly east, sets directly west. All right, but if you look at this in an infrared telescope, you see something totally different. In fact, over here on the left-hand side, you all see all kinds of activity that you don't see in visible light, that you need a different kind of telescope to use to be able to see these things. In fact, when we look at the sun, each kind of telescope sees different things on the sun. People often say, why do you have to have so darn many telescopes? That's because they're all tuned slightly differently. And we see all kinds of different things going on in the sun. Works the same with galaxies as well. We look at the Whirlpool Galaxy, in visible light, this is what we see. But if we use infrared light, we use radio waves, we use ultraviolet light, we see all kinds of different things depending on the telescope we use. And so, although astronomers sometimes seem greedy because they need so many telescopes, every kind of telescope tells us something very, very different. The Crab Nebula exploded in supernova 1592. 1054. I think I'm dyslexic tonight, right? Again, if we look in the infrared as opposed to looking in X-ray and ultraviolet, we see different stuff going on in there. So what I would advocate is not just that Saturn is fat, but rather telescopes allow us to see all kinds of things in the universe that we can't see before. And if we design our telescopes carefully, we see different kinds of things that our eyes can tell us about. All right, you started with Jupiter. Let's talk about Jupiter here. Jupiter has orbiting moons, and those are totally cool. But what we now know is when we look at stars around stars, sometimes those stars have planets orbiting around them. So this is a picture taken over Big Island at Gemini Observatory. Again, we're using this eclipsing technique where the central star, just like the sun is so darn bright, the star is really bright. So we block it out, and we're able to find, here in this case, 3 different planets orbiting around this star. People were amazed at this. You know, our solar system doesn't have 9 planets. That was a little dated. Our solar system has 8 planets. But hold on. We're going to argue this again this summer about what's the definition of planet. That's a whole other talk. Have me come back after this summer, and we'll figure out exactly where we are with this. That's a whole other talk. But here's Fomalhaut, Pisces Australis, where again, if we block out the central star, we can actually see here a planet that moves around in a short enough time span that we can actually see this on the sort of duration of the lifetime of a graduate student. So that's right. No one does that research anymore. Once you're done, I'm not going to do it. That takes too hard. So if we look at the number of the planets that have been discovered around other stars, I mean, at one point, all the planets we knew about were around our sun. Then we started to find a few around a few other stars. Then found a few more and a few more. And we started really accelerating here until now we know more than 3,000 confirmed planets. Not 30, not 300, 3,000 planets around other stars. I want to point out the color coding here is what's the strategy by which we find these things. And what's happened is our technology has allowed us to use what we call transiting techniques, which has really caused us to be able to find these things much, much more quickly. The way these things work is as a planet goes around a star, even if we can't see that planet, when the planet passes in front of the star, it'll slightly decrease the brightness. It's 0.1%. Now, that may not seem like very much, but even with a backyard 8-inch telescope with the right equipment on it, you can actually make these measurements. So everybody's in the extrasolar planets game right now. We're finding tons and tons of them. If I'd given this talk just 3 years ago, what I would tell you is that almost all the planets we're finding are giant, Jupiter-sized planets. Some Neptune-sized ones, almost no Earth-sized planets. But here we are just a few years later, and now that we're better at finding planets, we're not just finding the big ones anymore. Now most of the planets we're finding are actually Neptune-sized planets, 3 to 4 times bigger than Earth, but not as huge as like a Jupiter type of planet. So what I would propose here is not just Jupiter's got moons, but stars have planets around them. And it's very, very common. The planets aren't special. Our planets are not special, but rather planets are a natural byproduct of the way that stars form. All right, last one. Venus exhibits phases. And before we said the way we figured out that Venus must be going around the sun is because it started to look different. That sometimes when Venus is close to us, it appears big in the sky as a crescent shape. When it's far away from us, it's smaller, but it's much more round, much more close to full in shape. Well, if we start to look at our local neighborhood, the 700 stars closest to our star, the sun, we've discovered there's actually quite a bit of structure in how the galaxy's laid out. So there are places where you have lots of stars and places where there are not very many stars. Places where there are lots of stars, places where there are not very many stars. We tend to find this pattern of stars clumping together. As we look at galaxies, like this picture of the Milky Way, the Andromeda Galaxy, not the Milky Way Galaxy, good catch. So most of these white dots you see here are all foreground stars, stars that are in our own galaxy. Once we get past these stars, you got to go about 2 million light years before you get to the next group of stars, which is with the Andromeda Galaxy here. The universe, again, follows this pattern of bunches of stars, a whole lot of nothing. Bunches of stars and a whole lot of nothing. fact, we look at the structure of the universe as we best understand it. A lot of that work's been done right here in Hawaii. What we realize is that there are these places where we find lots of clusters of galaxies all clumped together, and then lots of empty space in between. In fact, if we look at microwave wavelengths of the light that was originally created during the original Big Bang, more than 13.7 billion years ago, we find is the universe was not created nice and smooth. We find there are areas here that are relatively cool, and areas here that are relatively hot. And these hotter areas are more dense areas. And these were the places where galaxies started to form. These were the places where there weren't any galaxies. These were voids. And just in the last few months, we've really begun to really focus in on this and begin to understand exactly the nature of light that was going on when the Big Bang happened. And that the universe is not created smooth, but rather it's pretty lumpy. And that's what resulting in what we see today. So what I propose here is the universe has structure. And that we can actually map that structure, and understanding the structure of our universe is really, really darn cool. So I propose that Galileo's 21st century syllabus would still include those original ideas, but we'd modify them a little bit to include some of the more modern thinking. Last thing I want to say here as we run out of time, something else Galileo would do if he were alive today is he would come to the Big Island's Science and Science Fiction Convention that's held every September. There's a bunch of HawaiiCon folks here. He definitely want to come over here. If you think this stuff is cool and you want to spend 3 or 4 days immersed in cool science and how it influences science fiction, this is the place to be. It's a totally, totally fun conference. And with that, thank you very much. Yes, ma'am.
So when stars form, the leftover remnant creates the solar system and the planet, the little particles that are put to accrete and make the planets, and then, wouldn't you say that it's possible that all stars as we know have solar systems that then create planets and have planets?
So what she was proposing was if when stars form, that the leftover stuff around the outside goes into making planets like our solar system, wouldn't it make sense that all stars that form probably also have planets? And the answer is probably almost not quite. So if a star is really, really big, when it forms, it creates a tremendous amount of energy. We call them T-Tauri winds. And they completely blow all the debris far, far away from them. So we don't think we usually see planets around those kinds of stars. And then the really, really tiny stars, which most of the universe is made of teeny tiny dwarf stars, when they form, they don't typically have enough gravity to keep all those things around them, and everything just kind of floats away from them. So our estimate's probably a third of the stars you see in the night sky have planets, but probably not all of them. But if we were just to find a star, if it would look like the sun, it probably has planets around it. Now, does that planet distribution look like ours, with some rocky planets close in, a couple of big giant planets in the middle, and way, way out some medium-sized planets? Theoretically, yes, but we haven't found a single solar system that looks like ours. So this is a place where we really don't know what's going on here. That people have suggested maybe these big planets always form where Jupiter and Saturn do, and then they migrate in closer, or sometimes they migrate farther away. We don't tend to find many solar systems that are structured exactly like ours. And we have no idea if this is dumb luck because of the way we search, or if our solar system happens really to be unique, which means that Galileo was completely wrong, that we aren't common, but maybe we are really unique. We don't know. So the question was, what's the current thinking about the number of the civilizations in the Milky Way? So this has actually been in the news just the last couple of weeks. I don't know if that's why you mentioned this. So it used to be we said, all right, how many solar systems are out there how many civilizations are out there? Well, that depends. How many Earths are out there, right? Well, what's an Earth? An Earth's a planet that's not so close to its sun that all the water boils away, and not so far away that all the water freezes. It's just right. We call it the Goldilocks zone, right? Not too hot, not too cold, but just right. Right? So how many planets are there? Well, 5 years ago, we didn't think there were very many planets out there. We said it's not possible, right? If there's not very many planets out there, then the likelihood that there are civilizations is like 0. Well, now we find that planets are very, very common. So now we're having to change our thinking about this. So maybe Earth-like planets are quite common. Now, what about intelligent life on those planets? Well, it depends on a couple things. Number one, how do you define intelligent life? The way astronomers traditionally define intelligent life is any civilization that can create and communicate via radio waves. So dolphins are not intelligent, but astronomers are. That's the rule, right? Because that's what we look for. We want to find a civilization, ancient civilization. We look for their radio signals. Well, what about us? Are we an intelligent civilization? Sure, we are flooding the universe with radio waves. And we've been doing so since about 1930. What about in 2030? I mean, how many of you listen to the radio in your car on your way up here? Not so many. Right? It's not common. My kids, they don't even know what the radio does in my car. Kids don't listen to radio. We aren't using much radio anymore. We're now using cellular. We're using microwave. We're changing the way we communicate. In another 10 years, we will likely be radio silent. Does that mean we are no longer an intelligent civilization because no one can find us anymore? We don't know. So is the definition of intelligent civilization one that communicates by radio waves? That's not such a great thing. The other problem we have has to do with lifetime. As soon as you're able to have the technology that allows you to communicate via radio waves, you will probably also have the same technology to completely destroy your civilization, destroy humanity. How long does humanity last? Well, let's see. What about let's use the example we know right here on Earth, right? So if you really are generous, you might say humans have been on the Earth since the last ice age, so 10,000 years or so, right? How long does a civilization last? Let's suppose we're really, really lucky, and we can last 50,000 years. That's pretty generous for how long we can. I mean, Rome lasted, what, 500 years? The United States been here for 200 years. Italy, been here for like 6 weeks, depending on how you measure it. How long does a civilization last? Well, let's just say a civilization can last 50,000 years. That's a really long time, right? But in a universe that's 13 billion years old, how many of those 50,000-year-old civilizations could have come and gone? Come and gone. So the problem really isn't how many civilizations are out there. The problem is how many civilizations are out there right now. The ones that have been there but are gone or are still to come that will be gone before they come up. That makes these numbers really, really fun to talk about. And that's a whole different class. You're welcome. The question was, what would, as he stalls, Galileo think about gravity waves? So, I mean, the whole world of astronomy has gotten itself turned upside down here in the last few years. Because now there's a whole new astronomy, right? Before, the way we learn things about a star, like the sun, I mean, we can't go to the sun and pick up a bucket of sun stuff and bring it back. It's just too hot. Even at night, right? You can't do that. So the only way we know anything about the sun is by studying the light that comes to it, the energy that comes to us, right? And in the last 60 years, we figured out it's not just visible light that's coming off the sun, but there's ultraviolet, and there's X-rays, and there's infrared, there's all kinds of things. Well, now come to find out there's a whole new kind of energy coming through the universe called gravity waves that are created in really, really violent things, like the collision of two black holes, right? Which you may think is a funny question, but every time I go talk to a fourth grade class, they say, what would happen if two black holes would fight? Who'd win? So this is not an unusual question astronomers have to deal with. But now we know when two black holes collide, they emit energy in the form of gravity waves. And so now there's this whole new field of astronomy called gravitational wave astronomy. And Galileo, have I stalled long enough yet? That's a great question. I have no idea. It is the new telescope. I mean, so if you look at what kinds of things are happening internationally right now, the Hubble Space Telescope was supposed to be done by 2001. It's still going, right? JWST was supposed to be launched in 2008, in 2010, and 2012. Now, at least we have a launch date for JWST. It's December 45th. But the next really cool telescope is the LISA project, the Large Interferometry. Help me out here, LISA. Basically, LISA is 3 satellites that are all positioned around the Earth, and they have very accurate laser beams that measure precisely how close those satellites are to each other. And so if a gravity wave comes through, they'll separate and close as that wave goes by, and we'll be able to very carefully measure that. That's the next really, really cool thing that's going to happen in astronomy, is this gravitational wave astronomy done by satellites. Now, when will that happen? Well, NASA has now backed out of that project, and it's all being done by ESA. So, well, we were talking about this earlier, right? I mean, did the omnibus pass today? Was Lisa in it? I don't know. So astronomers really don't want to worry about who's in the White House. I mean, it's fun to argue about it at barbecues and backyard hulas and stuff, but astronomers really don't want to worry about who's in Washington, D.C. But astronomy is largely funded by the federal government and your tax dollars. And who's in charge, whether it's in the White House, the legislature, wherever, makes a big difference in what astronomy gets funded. And so we've backed out of that at the moment. But that's where the next cool discoveries will be made in gravitational astronomy. So Galileo would be proud. He'd be happy. I think so. Yeah. Absolutely. He was interested in gravity in a couple of ways. One is this idea of imagining balls rolling down planes is what we talked to students about. But what he was really able to do was imagine a universe without friction, right? That if friction didn't exist, how would the world act differently? He could imagine a ball that would roll on forever and ever and ever with the law of inertia type thing, as opposed to the law of impetus, which is what Aristotle had been proposing. And of course, in terms of looking at atmospheric pressure, the invention of the improvements of the measuring atmospheric pressure, right, which had to do with gravity of the air pushing down. I think he'd probably think it was totally cool. I'm not sure he and Newton would have gotten along very well, but that's probably more Newton's fault than Galileo's fault. Thank you all so very, very much.